Sir, are you recording the meeting?
Ooh, thanks for reminding. My bad. Okay, somebody started recording apparently. Cool. Fine. Fine. So I guess I'll have to do something about whatever I missed. So yeah, we'll figure out. But let's continue the lecture for now. Okay. So you are stating the plan over here. Suppose for contradiction, right? The claim is not true. Okay. And then assuming that the claim is not true, you are coming to you are applying your proof steps and coming to some conclusion which is completely absurd. So here you are saying GCD of PQ is equal to 1 and you are also saying GCD of PQ is not equal to 1. So both of them cannot hold together. So that is a complete absurdity. That is complete nonsense. Right? And then you say that, okay, look, if you assume the opposite of what you want to prove, you get this nonsensical statement. And therefore, what you assume, your assumption must be false. Right? Your assumption must be false, which means that the statement you are trying to prove must be true. Cool. So that is a quick recap of how do you write a proof by contradiction or the inherent argument within such a proof, which I'm sure you all have seen earlier. Cool. Yeah. Now let us use this fact to prove something rather interesting. Okay, use the fact that square root 2 is irrational to prove something interesting. Okay, so the claim we are going to make is the following. There exist irrational numbers a and b such that a to the power b is a rational number. Any proposals? How would you prove this? Any ideas? Does somebody want to suggest something? Please raise your hand before you start speaking. Ramanuj? Ramanuj, yes, go on.
Yeah, sir. So in this, we can use something like root to the power root 2, say that is rational or say that is irrational. And then we can.
So you have seen
the
this
power
proof happen.
root 2. Yeah, I've seen this proof before.
Cool, cool. Okay, fine. I get what you're trying to say. Good. Okay, Manthan.
So if we can show one example where A and B are irrational and A to the power B is rational, then
fine. Yes. So what is an example?
Example. Yes. I'm thinking. Wait. I'm thinking.
Actually, you are thinking. Fine. Okay. Fine. So you can take this offline, and if you find an example, you can let all of us know. It should be easy to find an example. But what I'm trying to yes. Go on.
I remember it was taught in 8th class, and I found out an example, but I didn't remember now. I will find one thing.
That's fine. Take your time. No issues with that. Do it after class. Okay, and let everybody know if you find an example.
Fine. So I do remember iota raised to the power iota.
What? I'm looking for irrational numbers. I'm not looking for complex numbers. So irrational, I mean real irrational numbers. Okay, so I'm not sure what you're trying to.
So like, can we do a proof like this, that we choose A as some irrational, say root 2, and then like we say that, like, suppose we choose B, we start with B as a rational, and then we say like that root to the power 2 is 2, and then we choose the next, like another rational, like root 2 to the power 3, like, and we say that in between an irrational has something like that.
So you are kind of using some high heavyweight math over here, continuity of functions and so on, right?
Yeah, I'm not sure if that makes sense. So I was just asking.
Sir, 2 power 1 by root 3 and root 3 we can use, sir.
2 power 1 by root 3 and root 3. So how do you know 2 power 1 by root 3 is irrational? Right? So it might be, you might be able to prove. So take it offline, see whether you can prove. I kind of believe you, it might be irrational, looks quite irrational, but that needs a proof. okay, so like people, okay, let's get back to what we are trying to do. So like so many people said, if you actually construct, if you actually show, okay, if you actually produce two irrational numbers a and b, such that a to the power b is a rational number, then you're done, and that would be a proof by construction, right? So something we saw in the last class. So right now, what we are trying to show is a proof of a similar statement, a statement of the form there exists some object, but without actually constructing such an object. Even that is possible. So that is the point I'm trying to drive through this claim, right? So proof. So like somebody said, I forgot the name now. So consider the number. Consider the number square root 2 to the power square root 2. Okay, so the whole proof is going to rely on this number in some sense. Okay, first of all, I am not claiming that this is the number that we want. A is square root 2 and B is square root 2 is what we want. I am not saying that. All I'm going to say is this number, right? So this number is the two. Good. Right? Now the next argument, yes, Abhinav? Yeah.
Sir, as you said, 2 to the power 1 by root 3, we don't know whether it's irrational or not. Like we have to prove it. Then how do we say that root 2 to the power 2 is real only? It cannot be something else. It's rational or irrational. How do we know that?
So this, okay, I'm kind of assuming the fact that if you raise a non-negative real number to another non-negative real number, you get another non-negative real number. That is something I'm using over here, right? So yeah, is that okay, Abhinav? I mean, that itself is a non-trivial statement, I agree. But that's
Then,
some
sir,
kind of property of real numbers that I'm using.
2 to the power 1 by root 3 should also be an irrational number then.
Why?
Sir, 1 by root 3 is also a real number, non-negative real number. And 2 is also a non-negative real number.
Cool. So the 2 to the power 1 by root 3 or whatever you're trying to say is a non-negative real number. I agree. But why is it irrational? Or why is it rational? Whatever you are saying, you should prove, no?
Oh, okay. Okay, sir.
Right? I agree. It's a non-negative real number. Right? Okay, fine. So let's yes, Shrimanti, yes.
Sir, how do we come up with this number in the first place?
Okay, let's take this question after the proof. Is that okay?
Okay.
Good. Okay. So yeah, Darshan. Darshan, yes.
Hello, am I audible, sir?
Yeah, go on.
Sir, can we take the numbers as root 2 and root to the power 2 root 3 and b as 1 by root 3?
Okay. So let's do the following. In the interest of the time of the class, propose all your proofs on the discussion forum, and I'll be happy to discuss them.
Sir,
is that okay? Darshan?
Sir, I mean either of the cases, root to the power 2 root 3. If a is root 3 here and b is 2 root 3, then it will be rational or irrational. Two cases.
Yeah, I think you are giving a similar proof. I think you are giving a very similar proof. I think that something like that should work. Let's take this to the discussion forum. Is that okay?
Okay, thank you.
Yeah, cool. Yes, so this number is either rational or irrational. So case 1, if square root 2 to the square root 2 is rational, then what? Then we have constructed an example, right? So then take a is equal to b is equal to square root 2, and then a to the power b is going to be rational. Case 2, right? So if square root 2 to the power square root 2 is irrational, what do? Take a equal to what and b equal to what? Any suggestion?
Sir, root 2 power root 2 and root 2. Root 2. Sorry. So A can be taken as root 2 power root 2 and B can be taken as root 2.
Right, so A to the power B is square root 2 to the power square root 2 and whole thing to the power square root 2. So that is square root 2 ka squared, which is 2, which is a rational number. Okay, the point is this is some nice little example, but the point is we are not giving an explicit example. We are not even claiming whether this number square root 2 to the power square root 2 is rational or irrational. But all we are saying is no matter whether it is rational or irrational, look, we are able to construct an example. Right, so we are not explicitly giving one example which satisfies the criterion that we are looking for, and yet we are able to prove that there exists an object satisfying whatever property we are looking for. Okay, so this kind of a proof is called a non-constructive proof. Okay, Shrimanti, your question was how do you at all consider this kind of a number? That really comes from, I mean, it's really a matter of experience, right? So it's writing proof in general is not some automated thing. You cannot ask a computer to write a proof of a given theorem in general, right? So it really comes from experience. It's like asking how do I drive a car? Can I ever tell you over a lecture how you drive a car? You'll have to learn it from firstly from an expert. You'll have to keep practicing it. Unless you sit in a car and try to drive it, you are never going to learn how to drive a car, right? So it's more of a practice than teaching. These are the skills which really come through practice, and they cannot really be taught. Okay, although obviously the teacher can kind of guide you to pick up these skills over time. So, and hopefully that is going to be my aim for the next couple of months. Okay, cool. Any other question before we proceed? Okay, cool. Fine. Okay, so let us look at more proofs. Okay.
Excuse me, sir.
Yes.
Sir, can you tell once again that what do we mean exactly by a constructive proof?
So constructive proof is, the goal is to prove, okay, let me do it over here. So the goal is to prove a statement of the form there exists some x which satisfies some property p. This is the goal, right? Constructive proofs apply only when your goal is to prove a statement of this form. Okay, and how does the proof go? Right, so you give an explicit x and then show that p of x is true. That's it.
Okay, sir.
Right, so in this proof we did not give one single pair of numbers a and b which satisfies this property. All we said that, okay, look, this number, fine, if it is rational then I'll do this, if it is not rational then I'll do that. I don't know whether this is rational or not, I don't want to commit on that. Okay, so that's why this is not really a constructive proof. Okay. Whereas the proof that we saw in the last class, where you were asked to prove that there exists an intersecting set system of size 2 to the power size of s minus 1, you actually constructed the set system and then argued why it is an intersecting set system. Right?
Yes, sir.
Yeah. Cool. Cool. So good. So, okay. Claim. Suppose in a group of 6 people, I believe some of you have seen this earlier. I'll ask whether I'll find out how many of you have seen this. Okay, suppose in a group of 6 people, every pair of persons are either every two persons. Every two persons are either mutual friends or mutual enemies. Okay, so prove that there exist three people. Okay, either there are three people who are friends of one another, or there are three people who are enemies of one another. How many of you have seen this? How many? Raise your hand if you have seen this claim earlier, or are that the proofs? 4, 6. Okay. Okay, so let's say around maybe less than 20 people, I believe. Okay, cool. So then it definitely makes sense to discuss this in a bit of a detail, right? So all I'm saying is let's pick some 6 people in our class, and let's say each pair of you, right? So between every 2 people, there is a friendship relation or there is a relation of enmity, right? And now I want to claim that in this 6 people, there exist 3 people who are, okay, so either there exist 3 people who are friends of one another, or there exist 3 people who are enemies of one another. Okay. How do you prove this? Any suggestions? People who have seen this earlier could maybe they suggest if they recall.
Sir, I remember the proof, so I don't think that I should start narrating
All
it.
right. Fine, no issues, no issues. Right. So again, so the point in giving this proof is giving you one more kind of high level idea of how you could write proofs, right? So the details of the proof or this claim itself is not too important as far as the course is concerned, right? So our goal for the last lecture and this lecture is how do you, okay, what are the kind of templates of proof we'll be looking at, and how do you write them clearly? Okay.
Hello.
So yeah, yes, somebody's saying something.
We can start with if we will make a set where we will write all the pair of friendship and a set where we will write all the pair of enemies.
Okay, so F is the set of all pairs of friends, E is the set of all pairs of enemies, then what?
And let's name the people as 1, 2, 3, something like that.
Okay, let's call the people 1, 2, 3, 4, 5, 6.
Yes.
Then what?
And then we have to prove that the intersection of all the sets in F, the number of elements in the intersection of all the sets in the F, be greater than equal to 3, or either all the intersection in the E, number of elements in the intersection of V should be greater than or equal to 3.
Number of, okay, the size of the intersection of all sets, all pairs, what? Okay, what is F after all? One sec, could you define F and E formally? What is F?
F will be a set of pairs like 1 and 2, 3 and 4, like that. 1, 2, something like that. Yes.
Is that?
Yes. X, Y, where X and Y belongs to this set. 1, 2, 3, 4 cycles, like that.
And they are friends, no?
Yes.
Yeah. Okay. So then what? So define E analogously, and then what do you do?
then we will suppose there are two sets x1 y1, x2 y2, and x3 y3 dot 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 in F.
Okay.
x1 y1, x2 y2, x3 y3.
Okay. And so on. Some xm ym. Then what?
Then wait one second, just one second. Then there must exist three numbers such that y1 is yi equal to xj, where I is not equal to j. Xi equal to yj.
Is it going anywhere? Is it going anywhere? So, by the way, this claim is false if I just take 5 people instead of 6. Are you aware of that? So whatever proof you give should fail if you have 5 people, and it should only succeed if you have 6 people. Right? So if your idea is kind of going through, if you think your idea is working even for 5 people, then probably there is some problem with your idea.
Okay.
Okay. So just think about it, and if necessary, I'll be happy to discuss with you. Okay. So the idea is to use a principle that we saw in the last class, right? Which is the pigeonhole principle, right? So consider. Okay. So actually, yeah. Let's call the people. Okay. Fine. So consider person 1. Okay. So person 1, let's kind of isolate this person from the other people. There are 5 other people. And with each of the 5 other people, this person has a relationship of either friendship or enmity, right? So you have this person 1, and you have the other 5 people, 2, 3, 4, 5. So maybe one is friends with 2 and 3. Oh, sorry, 5 other people, no? Yeah, one is friends with 2 and 3, and one is an enemy of 4 and 5 and 6. Right? So since there are 5 other people and this person 1 can have one of 2 relationships with each one of them, what does it mean? So there are some 3 people with whom one has the same relationship. Right? So by pigeonhole principle, either one is a friend of at least 3 other people, or one is an enemy of at least 3 other people. Okay. Now begins the crucial proof technique. So this is nothing but what the book calls proof by cases. So we'll prove by cases. So prove by cases. Right. So what is the idea? So your idea, okay, high level idea is the following. You have some set, okay, S, and then you want to prove that for every X in S, some property P of X holds. Okay. What do you do? If it is convenient, you divide S into some smaller parts. Let's call them S1, S2, whatever, SM, some M parts. And then what you do is for every okay. So for every I going from 1 through M, you prove for every X in SI, P of X holds. Right. So this is the high level template of proof by cases. Right. And why do you divide into cases? So you divide into cases so that you can kind of provide a separate proof for each case. Using the fact that your X belongs to one specific SI, this extra kind of stronger property might be useful for you to prove whatever you want to prove. Okay. So we'll prove by cases over here. So what are the 2 cases? These are the 2 cases that we already identified. Right. So either one is a friend of at least 3 other people, or one is an enemy of at least 3 other people. There could be overlaps, by the way. Okay. In this case, there cannot be overlap, but in general, yes. As long as your SIs kind of cover all of S, that is fine. Okay. So what is case 1? one is a friend of at least 3 other people. Okay, so one is a friend of at least 3 other people. Let 2, 3, 4 be friends of 1. Right, so we are picking some arbitrary 3 friends of 1. One could have more than 3 friends, but we are picking any 3 friends of 1, and we are calling them 2, 3, and 4. We are naming them 2, 3, and 4. Right, so now what? So if any of 2, 3, 4 are friends of each other, any 2 of 2, 3, 4 are friends of each other, then okay, so any how should I say? Okay, let me put it a bit more mathematically. If I and J belonging to the set 2, 3, 4 are friends of each other, then 1ij are friends of one another. Right, so what are we saying? Let's kind of slightly modify this diagram and make 3 friends, have 3 friends of A of 1, right? So 2, 3, 4. Now we are saying if either 2 and 3 are friends, or 2 and 4 are friends, or 3 and 4 are friends, our job is done, because we'll just add 1 to that set and then you'll get a group of 3 mutual friends. Right, so for example, if okay, where is my mouse pointer gone? This is weird. Okay, so let's say 4 and 3 are friends, right? Others may be enemies, I don't care. Right, so 4 and 3 are friends. I'm saying that okay, look at those two people and add 1 to that set, you will get a group of 3 friends. That's it. Otherwise, what happens? Right, so else. So note that, by the way, note that I have kind of split this case 1 into further 2 cases. Okay, just keep a note of it. Okay, so now what happens if all 3, so then else what happens? All 3 of, or rather else 2, 3, 4 are enemies of each other. Right? So either there are 2 people in the set 2, 3, 4 who are friends of each other, or every pair is a pair of enemies. So now what do you have? So if in this case you just have that right, so 2, 3, 4 are enemies of each other. So this is what we wanted to do, right? So either there are 3 friends or there are 3 enemies of okay, 2, 3, 4 are enemies of one another, I should say. Right, and similarly case, okay, now my question is the following. Case 2, 1 is an enemy of at least 3 other people. Raise your hand if you can complete the proof for this case. Cool. Okay. Could you all lower your hands? Let's see. Let's find out how many people are sleeping in the class. Could you all lower your hands, please? People who have raised their hands, could they lower them, please, as soon as possible? Okay, cool. So raise your hand. Okay, raise your hand if you think you will not be able to finish this proof. Let's see how many people raise their hand. Okay. So about 1/3 of the class is sleeping apparently. People who did not raise their hand for either of the two questions. Okay. Okay, so there is some handful of people. Cool. So what we could do is the following. So the around 10 people who said they'll not be able to finish this proof. Well, this proof by itself is not too important for this course. The point is to illustrate the idea of the proof, the notion of proof by cases. So what you could do is during the tutorial session, you could ping me or one of the TAs and then we'll explain the proof to you. Okay, so or I can leave the proof as an exercise for you for now, and then in case you don't manage to do it even after trying on your own for a while, we'll discuss it during the tutorial. Okay, so exercise, complete the proof. Okay, good. Okay. Now probably the next proof technique that we are going to see is probably, or rather is no doubt the most important proof technique that you are going to use or need, not only in this course, but in whatever theoretical computer science you do in future. Okay, and I'm pretty sure you have seen this proof technique in before, right? And actually, I kind of revealed it in the title, in the topic of the lecture, which is the principle of mathematical induction. Okay, so. Okay, let's have a poll. Raise your hand if you have not seen the technique of mathematical induction earlier. Raise your hand if you have seen mathematical induction earlier, but you're not confident how to use it in practice. Okay, there is somebody. There are some people. Okay, cool, fine. So hopefully by the end of the course, you should be proficient in using mathematical induction to prove your claims. Okay, yeah, please lower your hands. I've taken note. Good. Okay, so good. So people have seen the mathematical induction principle earlier, which means people know the statement. So let me just, instead of asking you to state it, let me just write it right away. Right. So what does the statement say? So let if P is a proposition on what? Okay, so let me just for now let me just choose the set n natural numbers union 0 such that the following statement works. So such that 1 P of 0 holds, or rather P of 0 is true, let me state it that way, and 2 for all n in capital N, P of n minus 1 implies P of n, right? And then we say then Pn is true for all n in n union 0. Right. So what is a proposition after all? Proposition is any kind of statement which takes as input a number. So I am saying proposition on this set, right? The specific set. So it's any statement that takes an item from this set as input and it returns you a true or false value. Just think of it that way. Okay. So P of 0 is true. I mean, suppose P of 0 is true, and suppose you also have the fact that if P of n minus 1 is true, then so is P of n. Right? So if these two properties are satisfied, then you can actually conclude that P of n is true for all for all little n in the set natural numbers union 0. Another way of stating this is if S subset of n union 0 is such that is exactly an equivalent way, such that 0 belongs to S, and secondly, for all n in capital N, n minus 1 belongs to S implies n belongs to S. Then what do you say? Then S is equal to this whole set. Right? This is just another way of stating it. Okay. So again, as we did before, let us use this technique to prove something, and then let us kind of figure out a template of proofs which use mathematical induction. Okay. So the claim we are trying to prove is the following. Okay. So Prabal, your hand is up. Prabal.
Hello.
Yeah, Prabal. Yes.
Sir, can we use more than one number in the proposition like P, N, comma, K, something like
I'll
that?
come to that. I'll come to that. Let's just work with the very basic mathematical induction for now, and then we'll see several avatars of this mathematical induction: double induction, strong induction, whatnot. Okay, structural induction, all of them we are going to see. For now, let us just prove something very basic using the very basic form of mathematical induction. Okay, so the claim we are trying to prove is the following. So define. So for us, an L-shaped tile. Okay. So the problem is the following. We have a grid like this. So let me copy it to the current slide. Right. So we have a grid like this, and what we want to do is we want to tile it using tiles of a very specific shape. Right. So the tiles that are available to us have this shape. Okay, so we want to arrange such tiles on this floor and completely cover this floor up. So we don't want the tiles to overlap. Oh, by the way, I should specify that the size of this grid that we are trying to cover is 2 to the n by 2 to the n for some n. Is it possible to cover this kind of a floor using these kind of tiles? Vedant?
No, sir. It should be a multiple of 3.
What should be a multiple of 3?
Total number of tiles.
So what Vedant is trying to say is the number of cells in this grid is 2 to the n times 2 to the n. So which is what? 2 to the 2n, right? Yeah. So it's a power of 2. Whereas every tile covers exactly 3 cells. And therefore, it is just impossible to cover this floor using these kind of tiles. But is this a necessary and sufficient condition? So can you say that every kind of floor whose area is a multiple of 3 can be covered using such tiles?
No, sir.
No, sir.
You can't, right? You can't. Okay, so I hope you all see examples of this. Fine. So what we'll do is the following. So from this grid. From this grid, let us remove some arbitrary square. What now? I want to cover this entire grid except this square using such tiles. Of course, I can rotate the tiles, right? So 90 degree, 180 degree, all those rotations are allowed. Now, is it possible to cover this floor using these kind of tiles?
So you can
not be general for all n. For some.
Yeah, please. Raise your hand, and then speak. Yeah, unfortunately, if two people speak, I just can't hear anybody. Manthan?
I guess the answer will be differ for different n. For some n it may be, and for some n it can't be.
I'm telling you that the grid has size 2 to the power n cross 2 to the power n. It's not some n by n grid. It's a 2 to the n by 2 to the n.
Yes,
grid.
it will be.
Okay, so Manthan thinks it will depend on the value of n. Aval?
Sir, it will be possible.
It will always be possible?
Yes, for all natural number values of n.
N. Okay, fine. So let us write down your claim and then try to prove it.
I don't think so.
Okay, so the claim is 2 to the n by 2 to the n grid can be tiled with L-shaped tiles. So by an L-shaped tile, I really mean this kind of an object. Okay, so Aval, how do you prove this?
Okay, sir. So first, we'll consider the base case, which will be a 2 by 2 grid.
Okay, so you are using induction.
Yes, sir.
Why is 2 by 2 grid the base case? There is a even lower thing, right? I mean, I'm saying that n. Okay,
right,
so this
okay.
happens for all n in n union 0. This is the claim. Sorry?
Right. So it won't be true for n is equal to 0.
Why?
It's simply a 1 by 1 grid, which cannot be covered by 3 tiles.
No, but you are removing one square out of it, no? So it's an empty grid, so it can be covered with 0 tiles.
I'm talking about okay. Yes.
Right?
Right.
So
right.
I mean this. I really mean this for all n in natural numbers union 0. So I mean to say that the claim holds even for n equal to 0. Right? So let's write down the proof maybe. So what do you call this case? If n is equal to 0, then something happens. What do you call this kind of a statement in the proof?
The base case.
The base case. Very good. Yeah, the base case. So base case, right? So n equal to 0. What? 1 cross 1 grid with one tile. Sorry, one. I didn't even write it. What the hell? 2 to the n by 2 to the n grid with one square removed, one cell removed.
So excuse
can
me.
be tiled. The base case 1 cross 1 grid with one cell removed.
Sir, excuse me. Sir, can that cell be arbitrary or is it some particular cell?
Any one cell removed. So let me actually make it very clear. So let me just complete the statement and then I'll clean up the claim and so on. So one cell removed can be tiled with 0 L-shaped tiles. Okay, so let me clean up this claim. Two to the n by 2 to the n grid with any one cell removed can be tiled with L-shaped tile. Yeah, so there's an L-shaped tile. Yeah, okay, so there are some hands up. Arin?
Yes,
Arin,
sir.
what is your
No, sir, I actually forgot to learn that.
Good. Okay, fine. So this is the base case, right? So you write a base case. Then what? So somebody was telling me the proof, right? They can continue now. Who was telling me the proof? Was it you, Aval?
Yes.
Yes, sir, it was me.
Okay.
So then we assume that this proposition is true for n is equal to k for a 2 raised to power k by 2 raised to power k grid. Then we'll use this fact to prove this for k plus 1.
Okay, fine. So let me just slightly change the notation you're using. So induction hypothesis. Right, so this is the induction hypothesis, P of n minus 1. So what is P of n minus 1? 2 to the n minus 1 cross 2 to the n minus 1 grid with any one cell removed can be tiled with L-shaped tiles. Right, so this you are supposed to assume this, and then you are supposed to Pn. You are supposed to prove Pn. Yes, I will continue.
Yes. So then we can divide 2 raised to power n by 2 raised to power n grid into 4 2 raised to power n minus 1 into 2 raised to power n minus 1 grids by splitting into 4 equal parts.
Good. So let's do.
So do you get what I mean?
Yeah, I get what you mean. So you're dividing it this vertically into 2 halves and also horizontally into 2 halves.
Yes, sir.
Actually, let me just draw that. We take a bold pen. Right, so he divided the grid into 4 quadrants like this. Right, so now each quadrant is 2 to the. Each quadrant has size what? 2 to the n minus. Each quadrant has size 2 to the n minus 1 cross 2 to the n minus 1. Now what?
Okay, so now the removed tile will lie in exactly one of these 4 quadrants. So, for example, in the figure you have drawn, it's in the top left quadrant, the second quadrant. So what?
Okay, basically you can. Acha. So here for this quadrant you can apply the induction hypothesis directly. Good. Then.
Yes, sir. And for the remaining 3 quadrants, what we do is, for example, in this case, which you have drawn out, we can take the bottom left of the first quadrant, the top left of the fourth quadrant, and the top right of the third quadrant, and we can cover these up with a single L-shaped tile.
With a single L-shaped tile. Okay, good. So let's try to do that. Yeah, good. So his idea is to cover this up using one tile. Is that what you're saying?
Yes, sir.
Right. So he has placed one tile over here. So he has covered all this up. Now what?
Now all the quadrants are 2 raised to power n minus 1 and 2 raised to power n minus 1 grids with one tile removed.
Exactly. And therefore, by induction hypothesis, you can tile everything using L-shaped tiles. Yeah, okay. There are lots of hands up. Yeah, let me go through them one by one. Manthan?
Over.
Rishabh?
Sir, I had a different proof. So basically, what I do is construct a larger L shape using these L tiles, which has double the length.
Okay.
So now what I can do is place an L tile right next to this hole.
Ooh, awesome.
And then view this 2 to the n by 2 to the n grid
Good.
as 2 to n minus 1.
That might be possible. Rishabh, try writing this proof up and post it on the discussion forum.
Yes, sir.
Okay, please do it. Okay, Aniruddha?
Hello, sir. I had a different proof as well. So my proof involved coloring. So if you remove one tile from a 2 power n by 2 power n, you would have 4 power n minus 1 tiles left on the grid.
Correct.
Now we can prove by induction that 4 power n minus 1 is always a multiple of 3. So a 3 coloring of the grid exists And since the 3 coloring of the grid exists, we can color the tiles also.
Wait. What do you mean by 3 coloring of a grid?
So we can color. So since there are the number of tiles on the grid are divisible by 3, we can color each. We can separate them into 3 parts, and we can color each of them using one color, such that every L-shaped tile covers exactly 3 colors.
But this needs a proof, no? Just because the number of cells is divisible by 3, why can you say that, okay, you can color so that, I mean, actually you are making 2 statements which require a proof, which require a non-trivial proof. So try writing out the proof, try writing out your ideas on idea on the discussion forum. We'll take a look at it. All of us will take a look at it. Is that okay, Aniruddha?
Yeah. Thank you.
Cool. Okay, so now let us kind of complete this proof for now. Okay, so with any one cell removed can be tiled with L-shaped tiles. Okay, so what do you do now? So consider so divide the grid into 4 quadrants. Consider the 4 central squares of the grid. Okay. Let Q be the quadrant from which the cell has been removed. Right, so this is Q for us. Okay, consider the 4 central squares of the grid. Leave cover the 3 of them which are not in Q. So I'm talking about these 4 central squares. Okay, so cover the 3 of them which are not in Q by a tile. Right, so now use induction hypothesis. Use induction hypothesis to argue, or rather, sorry, by induction hypothesis, each of the quadrants, since each of the quadrants is missing one cell, right, and has size 2 to the n minus 1 cross 2 to the n minus 1, it can be tiled with L-shaped tiles. Shibashish Raut, you have a question?
Yes, sir.
Yeah.
Sir, am I audible?
Yes, you are audible.
Sir, in this case only, this 4 into 4 grid which you have drawn, after removing the leftmost corner, can you just show by a rough sketch how will you cover these with the L-shaped tile?
After removing what? So you are talking about the quadrant Q?
No, sir, to the right of Q, or anyone. After
anyone.
Yes, sir. After removing any one tile, how will you cover by the L-shaped tiles? Could you just show by a rough
Achha, so you want concrete covering? Are you trying to look for a concrete covering?
Yes, sir.
Okay, so let's do that. Fine, let's do that quickly. We have time for that. Cool. Could you mute yourself if you're done? Okay, thanks. Fine. So he's looking for a concrete covering. So now what? Let's do it quickly. So look at. So somehow with this new version of the board that I'm using, I'm not able to see my own pointer. It's here. Okay. Okay. So now let us try to cover Q, right? So what do you do? So again you divide Q into 4 smaller quadrants. Look at the 4 central squares, right?
Sir, not Q, sir.
Achha, you want to do this?
Yes, sir. Any of the other 3 quadrants.
Yeah, same argument. So let's do this. So divide it into 4 quadrants, right? So this quadrant contains the missing square. So what you'll do is you'll cover these 3 using 1 tile. Okay. Now you're left with these basically.
Okay, sir.
Is that fine?
Yes, sir.
Yeah. Okay. Any more questions? Okay, so well, what we saw right now is just the very basic version of principle of mathematical induction. Actually, the principle comes in several forms, and the underlying idea is still the same in any of these cases. Right.
Sir,
So what?
different form of PMI, because in the formula you told us it was n-1 implies n, and this is n implies n-1. So is it the same?
No. What? I'm assuming that a 2 to the n-1 by 2 to the n-1 tile can be tiled. Sorry, grid can be tiled.
Okay.
Right? So I am saying that, okay, put a tile over here, and then now we know by induction hypothesis that each of these quadrants can be tiled, and therefore the entire thing can be tiled. Right? So it is Pn-1 implies Pn.
Okay. Sorry.
Kushal?
Yes, sir, I had the same doubt.
It's the same doubt. Okay. Fine. So yeah, this principle comes in several forms. So another form of this principle could be what is happening? Is somebody saying something? Or am I getting some background noise? Let me try to mute all of you. Obviously, you can unmute yourself whenever you need. Okay, fine. Right. So if P is a proposition on what should I say? Okay. If P is a proposition on, let's, instead of n union 0, let's use the entire set of integers Z. Right, so this is the set of integers such that let's say some P m is true, and then the second condition is the same. If Pn-1 is true, then Pn is true. Then Pn is true for all n. What should I say? Right, so I'm talking about the integer line. Right, so I'm talking about the set of integers over here. Right, so this 0. Disable the line. Yeah, so this 0, 1, 2, -1, -2, and so on. Right, so for some integer m, I know that Pm is true. And I also know that if Pn-1 is true, then Pn is true for all n. All n in, I should say, Z. What can I conclude out of this? For all n, what should I write after this? What should I write over here?
N greater than equal to n.
N greater than or equal to n. Right, so I hope there's nothing difficult about this. Yeah, it's exactly the same idea, nothing different from it. Okay. Right. Okay. So there is another version of mathematical induction which is called strong induction. So what is the strong induction principle? So suppose again, so if P is a proposition on, let's go back to n union 0, such that first of all P of 0 is true. And now secondly, what do we have? So secondly, yeah, so for all n in n, right? So the instead of Pn minus 1 implies Pn, what we want to say is for all m less than or equal to n, sorry, for all m less than n pm, right? So if the statement holds for everything less than n, then that implies the statement holds for n. Okay, so then we claim P of n is true for all n greater than or equal to. Oh, okay, so for all n in n union 0. Right. So what? Right. So in terms of using strong induction in a proof, what is the only difference? In the usual induction, for the induction hypothesis, you said that okay, let's suppose Pn minus 1 is true, and then using only the fact that Pn minus 1 is true plus the facts that have nothing to do with the induction thing, you somehow prove that Pn is true. But here what we are saying is we are going to use the fact that P is true for all integers less than n, strictly less than n. And using all of these statements, we are going to prove that P is true for the integer n. Okay.
So
if we are able, yes, yeah.
So here is m greater than or equal to 0?
Yeah. Good. For all m less than n and m greater than or equal to 0, right? So Pm holds. Yes, you're right. Right. So this idea is called strong induction. Okay, and now we are almost out of time. So in the next class, we will use strong induction to prove something, right? So we'll convince ourselves that the basic principle of mathematical induction is really doesn't look like it's sufficient to prove our claim, but then using strong induction, you are able to prove the claim. Okay, so raise your hands if you have seen this kind of a idea earlier, the strong induction idea earlier. Okay, some of you have seen, but a lot of you have apparently not seen. Oh, wait. So I think if you raise your hand, it takes some time for me to be able to see that you have raised your hand. Okay, about half the class has, maybe slightly less than half the class has raised their hands. Okay, fine. Could you all lower your hands, and then people who have never seen this, seen the idea of strong induction in the past, could you raise your hands now? People who have never seen strong induction in the past, raise your hands. Okay, so there are some people. So we'll look at it. We'll look at one proof in the next class which uses strong induction, and then over the course we are going to use it once in a while. Cool. Any questions before we end the lecture? We still have 2 minutes, but then it doesn't make sense to start the new claim and its proof. Any questions before we end the lecture?
Sir.
Yes. Yeah.
So in the previous example, someone was saying that he wanted to construct a bigger L out of the L-shaped L. I couldn't understand his argument.
Okay.
Yeah, I'll post a better write-up later in discussion forum. Yeah, I'll post a write-up in the discussion forum.
Yeah. We are looking forward to reading your write-up, but from what I understood, he was saying, so from this kind of an L shape, right? So where this is 2 by 2 with one cell removed. He is trying to construct using such tiles. He is trying to construct this kind of an L shape, which is double the size, which is 4 by 4 with 1 2 by 2 cell removed. From that, he wants to use it to construct even bigger 8 by 8 grid with a 4 by 4 quadrant removed, right? So he wants to tile all such objects using the basic tile, and then somehow come up with a proof. So we'll see what he's trying to prove.
Yeah, cool, sir. Thanks.
Okay, fine. So it's 11 o'clock. Time to end the class. Chalo, see you on Monday. Lecture khatam. Tata, bye.